One, if you're not familiar with Stanford Data Ocean, it's a platform if you do want to learn how to do biomedical data science or bioinformatics and precision medicine. There are scholarships available. It's just incredible skill set that you can learn and get a certificate from Stanford. And then there's the My PhD for teams in order to extract insight if you're working with wearable data or omics and things like that. So just to give you some sense of this. So if you're not familiar with a lot of these, the content that I'll be alluding to tonight is much of it is from Stanford Data Ocean, although it will complement many of you who may be doing it'll be some other things that will help excite you and maybe give you a clearer mental model what all this is. Sometimes you're doing it by yourself, some things may not be clear. So let me get started here. Here's what I want to share with you guys. Let me get this out of my way. I'm going to try to get this done within the hour. That's my hope. And then use the last half hour, maybe the first part of it for questions, things like that. And then maybe the last part of it, this would normally be an office hour. And so if you have questions, you want to chat about something, you can ask questions at the end, or if you want to hang out a little bit at the end, ask questions about a specific project or about Stanford Data Ocean or about a module you're working on or career decisions, whatever it is, I'm going to be there for you at the end. So the goal is to try to have us finished with this by 6. And then the last part will be questions and things like that, discussion. So I hope, feel free to put things in the chat if you go. We have a relatively small group, so again, don't worry about interrupting me. If you have something to say, I hope that you'll just unmute yourselves and jump in. Like I said, my goal is for you to get a really good, solid foundation on these things. So if something's not clear to you, or if you have some question about something, I hope that you'll feel comfortable enough to ask. Okay, so let's get started here, you guys. So we want to talk about machine learning, you guys. We want to look at what we did before we did machine learning, and that is traditional software development. And some of you may know anything that we wanted to do, we had to code it. And so if you want to know a person's max heart rate, you can have a person exercise to exhaustion, or you can have the machine calculate it. And so you'd have to code it. So you just want to say, my screen is, give me just a second. Here's this is spinning for me. Just saying, let me wait for this to stop here. Let me see if I can get through this while it's doing this. I don't know why it's. So you're going to say, machine, I'm going to give you an input. I want you to give me an output. You may give the machine age. And the machine doesn't know the relationship between age and max heart rate. So you might tell the machine, I'm going to give you this number 220. And I want you to subtract age from it, and the machine will give you max heart rate. Okay, the machine will faithfully do that. Similarly, if you want to know a person goes to the gym or the doctor and they get their BMI, and they say, what does this BMI mean? Okay, so you're going to, again, the machine doesn't know anything. You say, machine, I'm going to give you an input, you're going to give me an output. The input might be BMI. And so now it might be rules that you tell the machine. So you might say, machine, here's what I want you to do. If that number, because the machine doesn't live in our world, it's going to say, if that number is less than 18.5, put underweight into status, and the machine will do that. Otherwise, if that number is less than 25, put healthy into status. Otherwise, put overweight into status and return status to the user. And the machine will do that faithfully. And that's what we had to do for the longest time, you guys. We had to code anything that we wanted to do. But the machine is limited by your intelligence. And a great example of that is this. How in the world would you code a machine to tell the difference between a normal chest scan and someone with pneumonia or someone with COVID? What rules would you write? If it's from a different hospital, they may have a logo on it. There may be different contrast. How in the world, how would you code this problem? Better example would be, how do you tell the difference between a cat and a dog? That's a classic problem. Now, a 2-year-old can tell the difference, but how do you tell the difference? Okay, I want to tell you before we got to machine learning, why machine learning has changed the world forever. Will never be the same again. And it's this, if you wanted to code this problem, you might say, some people think of whiskers, the whiskers on a cat. Okay, cat has whiskers, dog also has whiskers, but a cat might have more prominent whiskers. So you might look at the whiskers, the cleft in the cat's mouth or the eyes. I think of a cat having maybe erect ears and a dog having floppy ears. So that might be the code that I would write if I wanted to code this problem. But the thing is, what happens if a cat has floppy ears? The code breaks. And software has to always be right. And here's another thing. What if you don't see the ears? I don't know how I can tell that that's a dog, you guys. I have no idea. Versus writing rules to say that that's a squirrel or a bear. I don't know how to tell the machine that. I know when I see it, but I don't know how I would code this problem. Okay. Some cats and dogs can be very big and fluffy, or some cats and dogs can be very small, not have any hair at all. Okay. So it can be difficult to code, but let's say that you wanted to do it. Okay. You said, you know what? I got this. I stayed up all night. I totally know how to solve this problem. I stayed up all night. Here's what I'm going to do. And let's say you came up with something. You might say, well, machine, if this is true, and this is true, and this is true, and this is true, it's a cat. I think I totally got it now. Otherwise, it's a dog. And if you could do that, the machine would say, oh, okay, so that's a cat and that's a dog, guys. But we know that hand-coded rules don't work. That's why when machine learning came on the scene, you guys changed everything. The coolest, most magical, creative problem, the things we pay more for are going to come from machine learning. We can't code them. Okay? You can't tell the machine what a cat and dog looks like. You know what's wild to me? How in the world can only your face unlock your phone? I think that's crazy. How would you code that problem? What rules would you write to differentiate your face from the billions of other faces on the planet? I think that's crazy, but that's what machine learning can do. Your job using domain knowledge is to come up with just a brilliant question and collect examples of the world and let the machine learn it. That's what we do. Everyone's chasing examples, data, because that's what machine can learn from. And you'll see what I mean here. Now, let me ask you guys a question. Okay, and I really want you guys to do your best to answer this for me. I want to give you guys a really good sense of machine learning. Okay, here's some examples. Here's an input. Remember I said you're going to give the machine some input? You have 144, 181, 200, 317, and 800. Okay, this is the associated output. 256, 219, 283, and negative 400. I know a few of you, so I know you're bright. Can anyone tell us what's the function? What's the relationship of what we say in machine learning? What's the function? If I were to give you another number here, could you tell me the appropriate number, the correct output? Anybody? If not, I'll tell you in a moment. But can anyone see it? What's the function? What's the relationship? Can you see it from looking at these numbers? I'll give you guys a few seconds here. Anybody can unmute or you can put it in the chat. If not, I'll give you a few more seconds and I'll tell you. Come on, somebody can see this. If I gave you a number here, could you tell me the correct output? Can anyone see it? 10 more seconds, you guys. Okay, the relationship is 400 minus the input. And if you're trying to solve it, whatever your brain was doing, that's how machines learn. I want you to take that with you guys. That just changed everything for me in terms of how I prepare machine learning, the question that I ask. That's how machines learn. Whatever you were doing, the machine says, you give me the input and you give me the output and you let me learn the relationship. Remember what we used to do? We'd give the machine the input, we'd code the relationship. Oh, machine, here's how you determine BMI, okay? Or here's how you determine someone's max heart rate versus getting them on a machine and exercising to exhaustion. That's what we used to do. We don't do that now. The machine says, you give me the input, you give me the answer key, and you let me learn the relationship. That's machine learning. And the way that relationship is learned with these beautiful algorithms have nothing to do with you. Machine learning is not you. Don't be intimidated by machine because it's not you. Your job is your whole task, because you live in the world, your job is to describe the world to the machine, ask a brilliant question, and collect examples of the world and get out of the machine's way. Okay? It's these algorithms have nothing to do with you. There's no one best algorithm. They all see the data differently. One will be best for this problem, won't be the best for the next problem. But it's the algorithms that sit in between your examples of the world that you're going to collect with your brilliant question, whatever it is. And once you do that, you know what the machine's going to say? Oh, you know what? I think I see it. It's 400 minus the input. Normally it's a black box and we can't see it in it, but we call this a model. That's a model. We call that a machine learning model, just like how your head sees a model. You know, like, oh, there's Francesca. Here she comes. Hey, Francesca, come on, we're going to lunch. There's a model that says that she is. That's what she looks like. Or there's a model for music that gets your head to nodding or makes you cry when you hear that song, or where you absolutely have to go dance at that song at the wedding, or makes you work out harder. That's a model. Your head hears music. There's no such thing as good as a good song or an attractive person or anything. It's what you determine. It's only a good song to you. a person you find attractive, or a dish that you would like. That's what machine learning model, every machine learning model is bespoke just for you. And that's what it's learning. It's watching you. Playlist some stuff. I'm watching you. Are you scrolling on TikTok? Are you lingering? Oh, you're looping it over and over? That's going to influence what you get served next. That's machine learning. If you could scale and go listen to every song ever made, what 30 songs would you bring back to you? That's what a machine learning model. It's your surrogate if you could do it. You can't scale. You can't go watch every movie on Netflix. So you're telling the machine, you need to learn what I would do. If I could, go bring back some movies that if I could, that I would bring back to myself. That's what a machine learning model is trying to do, is this model. So now we give it something, whatever this input is, it's going to give us this output. You're going to say, isn't that incredible? How it knew I would like that movie. I'll never pick that movie for myself. It's the cutest movie. I watched it twice this weekend. Just found this jewel of a movie I would never have picked. That's machine learning. I just think it's incredible. It's beautiful how it allows us to do things we could never do before. You can never code in these things that are interesting. You just can't. But a machine can see everything all at the same time and can learn things that you just can't do as a human. But we have to work together because you live in the world. That's why the machine needs you. But the machine can see 10 million rows all at the same time, and you can't do that. So you're co-equals. Okay, but this is what we call machine learning model. That's what it's learning. So the whole of machine learning, you guys, as I was showing you with those numbers, is to learn some unknown function. I gave you input, I gave you output. You have to learn the function. That's machine learning. The machine just said, no, you playlist some stuff. Let me just watch you. Skip some stuff after the first 10 seconds. No, I'm going to watch you, and I'm going to learn what we call a model. How your head hears music. That's all the model is. Okay. So the whole machine learns to learn some unknown function. That's all a recommendation system is, or Spotify, or Netflix, or Apple Music, or Google serving you an ad, or whatever it might be. That's all it's doing. Okay? So it says, you give me X. X could be height, weight, gender, race, and I'll tell you if a patient has diabetes. Or you give me a bunch of pixels in an image, and I'll tell you if that's you in that picture, whether I should unlock your phone, or you give me a bunch of words in a tweet, and I'll tell you the sentiment, if that person's angry, neutral, or delighted in that tweet. Whatever it is, that's what machine learning does. Okay? You give me X, and I'll give you Y. We say it models the relationship between the input and the output, or it models the relationship between X and Y. Okay? Let's go back to our cat and dog problem. Okay? As much as you think you can solve some of these problems by coding, you can't. The most interesting problems today, you can't code them. The machine says you can't tell what a cat or a dog looks like. I appreciate you trying, but you can't code it. Your job is to give me as many examples as you can. That's your job. And give me an answer key. Give me labels. Label in your world what you consider a cat. On a different planet, it may be considered, you tell me about your planet. That's what the machine wants to know. You might say, oh, okay, machine. Yeah, see, this is a cat, and this is a cat. And so the machine's looking at this. Remember, there's some algorithm sitting in between your examples of the world. And that algorithm's going to say, that's a cat, huh? Well, that's a cat, huh? This dark thing down here, that's a cat? Come have to learn, okay, and that's a dog, and that's a dog, and they have floppy ears. It's going to say, this dark thing right here, that's a dog. I'm going to have to learn it. Can't tell me. You just have to get out of my way and give me examples. That's machine learning, you guys. And once it does that, we call that a model. And the model holds all the information about the relationship between the input and the output. It's a thing. Once it's learned, it's a thing. That's what that model's a thing. Put it on a thumb drive. Give it to the team across the hall. Put it on your phone. Put it on a server somewhere. Share it with the world. This insight that you trained on your little computer, share it with the world. It's a thing. And so now we have this model. And the model, whatever you trained it to do, will say, go out anywhere in the world, go out anywhere on the internet, you get me a cat or a dog. It's never seen that before. But if you trained it well, it would say, definitely a dog. Now, machines think in terms of numbers, so it might output a 1 for a dog and a 0 for a cat. And the thing, you guys, a machine learning model should do one thing excellently. Can't give you directions, can't recommend a restaurant, but it can tell you whether it's a cat or a dog in the image. Okay? Now, the first take home that I want you to send you with for this. Okay, my hope as we go through this series, if you're at other talks in this series, is to build a foundation. So as you get to the end, it should be crystal clear for you a lot of these types of skills and understanding, especially if you're working through your certificate. Some of this you will go through on your own, but hopefully it will kind of supplement that, and that light will come on for you. Okay, so here's the first take home. Instead of programming a computer, you give a computer example and it learns what you want. That's machine learning. Okay. Examples of the world. That's all the machine says. You say data. If I'm talking to students, I don't say the word data unless they're in computer science or some. I say examples. If I had an undergraduate biology student come up to me and ask me, for my senior project, do you think I could do machine learning? I wouldn't say a thing about algorithms. I wouldn't say a thing about it. I would say, can you get examples? And she might say, oh, yeah, oh, well, you can do machine learning. That's all the machine. Machine doesn't know what data is. It's examples of your world. You give me examples of your world and ask me a brilliant question. And depending on the algorithm, like a neural network can learn just about anything with enough data and enough time. We're just in a different world, you guys. We're limited now about the amount of data we can collect. Because that's what the machine wants, just more and give me more and give me more. That's why we have these large language models with ChatGPT are getting so good at almost, I don't say replacing us, but in some ways, in terms of creativity, machines are outstanding because they've seen everything and they don't forget anything. You forget stuff. You'll take a class, 2 or 3 weeks later, you might remember 10 to 20% of the class. The machine doesn't forget anything ever. So machines are really good at what they do. Okay, so I want to give you a good sense of sometimes your job is to describe the world to the machine, collect examples, ask a brilliant question, and move. Get out of the machine's way. Now, let me give you a mental model. This is for me. What really helps me. One thing I hope that you guys don't do is memorize. One thing I really hope you guys learn, when you're learning something new, don't get in the habit of memorizing it. Okay, unless you're taking a test. I don't have a grade to give you. If you're trying to pass the test, maybe memorization work. But if you really want to learn it where it's yours, you have it locked down. Someone can wake you up at 3 in the morning and you could jump up and talk about it. Don't memorize it. Try to have a mental model of it. How does it work? It's almost like if you get in a rental car. Here's how I think. If you get in a rental car, your air conditioning turns this way and theirs flips up. You have to get a mental model. Or you're walking in the mall and you kind of bumped into the door because you thought it pushed, but your mental model was pushing with the doors to pull. It's the same thing here. If you can see it, it's yours. And so here's my mental model for machine learning is this. There's a term called pareidolia. I don't know if you guys know what this term is, but pareidolia is where humans, biologically, we see patterns. We do, like a baby recognizing mother's face. We see patterns. Just as what we do. So as a human, there'll be clouds in the sky, but you might see a heart because we see patterns. A dog or a bird wouldn't see a heart. We see patterns. You cut open a piece of fruit, you might see something. Or like this. This is how I envision machines learning, trying to see patterns when the machine says, oh, now I see what diabetes looks like. Oh, why didn't you say so? Or I totally see what your music looks like. Now I see what you're into. Or I totally know the TikToks I'm going to give you next time. Whatever it might be. That's what machines are trying to do. This is my mental model. Can I give it enough examples of the world till the machine can see it? Can you see the music I'm into? Can you see where we might enjoy staying this summer in Europe or whatever I'm asking the machine, whatever it might be? Because the machine knows it all. Everything, 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 everything. Been trained on everything. And so it's a matter of me asking great questions of the machine. Okay, so let me give you an example here in terms of learning the relationship. I'm going to ask you guys a question again. If you don't answer, I will answer for you. I hope you guys aren't bad for you guys by the time we're here because I'm rooting for you guys. My background is originally in physiology and I kind of transitioned into computer science. So I remember the beginner's mind in some of these types of things. So I'm so rooting for you. So I want to tell you, if I had someone sitting next to me and I had to learn this over again, that's where I come from. I just want you to lock this down so it changes whatever your trajectory is, wherever you're going. Okay, so learning the relationship is this. And I want to show you why having more data is important. Here we have your work for a company. You're the machine learning algorithm for a company, and this is or an organization, whatever, and this is their data. Okay, 1 and 2 and 2 and 4. Can anyone tell me what the function is? If I were to give you a number here, could you tell me what the output is? Can anyone see the function? And this is an easy one, you guys. If you're not gonna, I'll just have to tell you if you're not, but I want you to see it. This is for you, not me. Well, that's the algorithm, but what's the function? In other words, if I were to give you any number here, could you tell me the correct output? Allison, boom, boom, boom. Excellent. Yes, 2x. Allison, you guys go home, data team. Great job. You guys take the rest of the day off. This model is perfect. She solved the problem. That's the function. Okay, that's what I want you. That's the now it's a different company. That's their data. What's the function? Somebody? You can unmute if you want, or you can put it in the chat. If not, I'll tell you. Now I know you guys being back, so I know you guys can see this. What's the function, you guys? If I already give you another number, can anyone see the function? 5 more seconds.
I can tell you, but I did the last one, so
No,
it's
no,
Allison.
say it. No, say it. It's all right. Say it again. You're going to be my
Looks to me looks to me like x squared plus one.
boom. Man, I want you on my team. X squared plus one. Exactly. X squared plus one. So again, great job. Oh, you wait. We're going to change the world, you guys, team. Great job, data team. You wait till we release this on the world. We've learned our data. This is the data. That's all it can do is learn from examples of the world. Let me show you one more. And someone else, Allison, if you want to answer for everyone, then you're going to be the one who most. Oh, thank you. Yeah, Mohammed got it right also. Excellent. Last one. Here's another company. This is their data. What's the function?
The square of the input.
Boom. And that company's happy. All those models were excellent. They maximized the examples of the world that you gave them. But you know what happened? You put them out in the world, they're about 98, 99%. And you put them out in the world, 64%, 72% accurate because they don't have all the data. What's the master function? The Googles, the Amazons. That's why we hoard data. What about the company has all the data? Why are they always right? We've been working this problem for 6 months and they came in and why are they so good? They have more examples. Can anyone see the master function? This is tricky, but can you see it? If not, I'll tell you. So you think I'm just going to lean back? I'm not going to let you do that. Anyone? If not, I'll tell you. It's tricky, but I know you can see it.
Yeah, it's every other number is x squared plus one or just squared, but I don't know how you
Boom.
express that as a
That's it.
function.
No, Bill, that's it. That's exactly it. You guys, what Allison, to her big brain, is what a machine learning algorithm does. She's looking at examples of the world, and she says, I see it. I totally get the movies you're into. I totally see who you should go out on a date with if it's a dating site, or I totally see the restaurant that you should take your daughter for her birthday. Whatever it might be that I'm asking it, I get you. And that's what her brain is doing. She's just looking at numbers. Everything the machine sees is numbers. I don't care if it's language, text, video, medical data set, health, all of it's numbers. The machine's doing what Allison's big brain is doing. It's just looking at it until it says, I totally see what malignant cancer looks like. Totally see it. Or what fraud looks like. And so here's what Allison was trying to say. This is called the modulus operator. When you divide two into a number, it gives you what's the remainder. If it's an even number, the remainder is zero. It's x squared, as she said. If it's odd, the remainder is one. It's x squared plus one. That's the master function. And the only way you could learn it is to have all the data, to have more examples of the world. That's why I want you to say having more data is I'd rather have more data than the sexiest algorithm. Whoever has the most data wins. Period. That's what every company is chasing right now, is having more examples. That's what it is. If you ever hear anything about ChatGPT and getting examples, scraping this site and because they can't get enough examples to improve the models. That's how machines learn. Okay, so beautiful. Thank you, Allison. That's what I want you to get in terms of why you need more examples of the world. Because each company was correct on the data that they had, but they didn't have as much data as Google or Apple or some other university has or whatever it might be. Whoever has the most data wins. Okay, now let's talk about model training. The way we train a model, this is you. It's the only reason the machine needs you because you live in the world. You collect you ask a great question, come up with examples. You want to know something about patients? Can you get that data? Can you get examples of a patient doing that or their genomic data or whatever it might be? Can you get examples of your world? This is you. It's the only reason the machine needs you because you live in the world. It's the only reason the machine needs you. There's some algorithm here and it can see everything. You can't do that. So you two are co-equals. You work together to form a model. And the model doesn't live in our world, so initially it makes a random prediction. It doesn't know if it's right, but you're smart enough to give it an answer key. That's what you're going to do. You're going to give it an answer key. Now the machine can say, oh, you know what? I did not think that you'd like this song, Allison. I didn't think you'd like it. And I didn't think you'd like this song. You know what? I sure thought you would love that song. And the machine's going to change its internal parameters. That's all it does. Machine does not know that it's learning. It's an optimization problem for the machine. The machine's just trying to be a little less wrong each time. That's it. It so wants to please you. It's just trying to be a little less wrong each time. And before you know, it's going to say, I've minimized my error. We call that learning. She does not know it's learning, but it's minimized its error. Now it says, totally get the music you're into. You wait till next Monday. I have 30 songs I'm going to recommend to you. You're going to love them. That's what the machine is doing. Because you gave it examples. It doesn't know what a cat or a dog or a good song is or cancer or diet. It doesn't know anything but what you tell it. And it will learn that. And then we call that a trained model. That's what gets deployed. That's what's on your phone to unlock your phone. That's what's on some server to tell you if that's your credit card transaction should go through or whatever. It's a trained model. It knows that thing, whatever that thing is that you trained it to do. Now, normally we don't have just one algorithm. We'll have a bunch of them because there is not one best algorithm. They're all different. They all see the data differently. And whichever one performs best this time will be the one you choose this time. Probably won't be the one next time. And a lot of people ask, okay, which should I start? Which is the best algorithm? There's no such thing. They all just see it differently. And we won't talk about that here. But if you can walk through that, you say, oh, that's how that one's doing it, huh? Oh, that's how that one is making its predict. They're just different. And whichever one performs best, let's go with that one this time. Probably won't be the same one next time. Okay? Now let's talk about how do we evaluate a model. You've done a great job. You've come up with a great question. You're going to change the world. You've come up with a great question. Okay. And you've given examples of the world. Okay. You collected data. And now you feel pretty good about what you're doing. But how do I evaluate it? How do I know if it's really doing this thing? Well, we almost never use all of our data. We split it up into training and test sets, maybe a 70-30 or 80-20 split. We'll hold a little data out because we don't know if the machine is memorizing. The machine might start to memorize. You have to say, machine, I can't show you every image of me. I have to generalize what I look like. I might have shades on tomorrow. I might have a hat on. Might gain weight, might lose weight. Maybe I don't have my makeup on today. Whatever it might be, you got to generalize what I look like. I can't show you every image of me. And that's what the training set has to do. I can't show you every cat ever. I can only show you some. Just like a child. Child just sees some, then the child knows what the cat is. You don't formally typically teach the child that thing. Child learns from examples. It's the same thing. So machine, I don't know if you're starting to memorize because it might start to memorize. For example, if you take a picture of yourself with your phone, I'll tell you what overfitting is, and this can happen. If you take a picture of yourself with your phone, you might have a little micro scratch on your camera lens that you can't see. And the machine may learn, every image I've seen of you has this little micro scratch that you can't see. So when I give you an image of me that wasn't taken with my phone, you don't recognize me. That's what can happen. It starts to memorize. It's looking at just the examples that I gave it and I'm saying, no, the machine can't do that. You have to generalize your understanding. I think of it like this. If you were in college, you're preparing for final, your professor may give you your midterms back, and you may make flashcards. That's your training set. You're going to go through your flashcards. Some will be right, some will be wrong. You're studying them. That's the training day, like the machine's doing. You're going to turn them over. Oh, I got that one wrong again. And then before you know it, you're going to kind of know them. But are you memorizing your flashcards? Or you generalize whatever the professor gives me, I'm ready for my final. The only way to know is go sit for your final. If you've been like me, you sat for a final, you didn't recognize anything. You feel like getting up and walking out of that thing. Okay. So you don't want the machine to do that. You want the machine to generalize its understanding. And so what we do is we hold some of the data out, maybe 20, 30% of the data. And we get one shot with the test set. If it doesn't do well with the test set, we shuffle the data and start over. You can't look at the test set, oh, let me adjust some things and go back. It's spoiled once you use it. So we're going to put that test set out of the way and we're going to train on the training set. Remember, just like Allison was doing. She was a machine learning algorithm. She looked at that data and she processed it just like a machine will do for whatever question you ask it. And she says, totally see it. Totally get it. Totally get it. That's the training set. But I don't know because I didn't give her a test set that she hasn't seen. I didn't give her another number and see if she could. No, she kind of told me, and this wasn't as complicated. But now I'm going to go get that test set. I'm going to cross my fingers. And Allison might say, you know what, machine, here are 30 songs. I only like 3 of them. Find the 3 songs that I like. Or there's 10 pictures of me. There's 10 pictures here. I'm only in 2 of them. Find me. And if the machine can do that, we put that thing out in the water and knows some things. That's what we're trying to do. Okay? So machine learning, this is you. Brilliant question, collect examples of the world, plus an algorithm. Machine can see it all that you can't do. You two work together to form a model. Now I have to trust it. I don't know who's going to walk in the door tomorrow, but I have to trust that this model can predict the future for me. Something about a patient or an outcome or whatever it is that I want the machine to do. That's what we're doing. Okay? So that gets you up to this. Now, let me pause. Do you have any questions? Because sometimes it may be hard for people to jump in because you maybe think you're going to interrupt me. Before I continue, any questions at all? Let me pause for a quick second. Okay, now don't be bashful. Either stop me or put something in the chat. Let's keep moving here because like I said, I'd like to finish within the hour. Now, the next thing I want you guys to understand, and as I said, you guys, I don't know what you do, but there's not a thing you do going forward that machine learning won't touch. So I think it's so important to have a mental model of all of this. Let's talk about the types of machine learning. There are two primary types. There's others, but there's two primary types that we talk about. Here's what I envision for you. I don't know whether you're going to do this, whether you want to do this as part of your career, or maybe you're a manager, you just want to be conversant, be able to talk to a data team, or maybe you'll give a talk at a meetup, or you're kind of peripherally kind of interested. I've heard a little bit about that. Maybe I want to steer my career toward bioinformatics or biomedical. I don't know where you're coming from, but I do know it would be helpful, whatever you do, to be conversant about machine learning. Just be able to understand. Maybe read a technical article, or you'll read something, or you'll listen to a TED talk, or whatever it might be. You're conversant about it, or there's something you want to do, and you may want to communicate it with someone who does know about data. So here's what I want you to understand. There's two things I want you to understand: supervised and unsupervised learning. Okay, those are two primary types. There's other types, but these are the two primary types that you really would want to know. Here's your data now. This is toy data. You're going to have some data set you might be interested in. Okay, again, not to pick on Allison, just like Allison, you're going to have a data set. You want the machine to tell you something about that data set. Whether it's a playlist, you want to say, machine, go bring back some more songs that I can enjoy, or I have some company over this weekend, give me 2 or 3 movies that might be interesting, or I have some cousins coming in town, tell me something that I can make that a varied audience would all be enjoy, or whatever it might be. Because you're going to have some data set. You're going to want to ask it a question. You want it to understand your world. So in this case, here's what I want you to understand when you have the data set. Okay, this is structured data that's in rows and columns. Okay, unstructured data is not in rows and columns. Music, text, video, tweets, that's unstructured data. That's the world of deep learning. We're talking about structured data, just traditional machine learning. So you say, machine have this thing we call age. I know you don't live in our world. I know you know what age is. Just this number. Okay, we have age. We have this thing called sex. We have the type of chest pain. We have resting blood pressure, cholesterol, max heart rate, angina. And so we have all the in heart disease. The first thing the machine's going to ask you about your data set: what do you want me to predict? You say, oh, yeah. I want you to predict whether someone will have heart disease or not. You might want to predict someone's sex, or the type of chest pain that they're presenting. What, the machine doesn't know. Okay. Oh, yeah. I want you to predict whether someone has heart disease. That's called the target variable. And giving the machine a target variable is what makes it supervised. Okay, you're giving the machine an answer key that it can learn from, like a child when you correct a child, or like you when you're looking at your flashcards and you have an output, you have a correct answer to correct. Your learning is being supervised. Okay, do you have an answer key? Do you have examples? Okay, this is what makes it supervised. Okay, everything else in data science, machine learning, we call features. You may know them as columns, independent variables, fields, descriptors, all of that. But we call them features. This is all the machine knows about the world. The machine says, I'm trusting you. You live in the world, I don't. I'm trusting that this is all I need to know about your world to make a prediction. Now, if there's something else I need to know, you better tell me. Okay? Don't ever tell me more than I need to know. Don't just tell me stuff, but don't ever tell me less either. And that's your task. Is when I want to know that if I could scale, do I really need to know that? Or is that just noise? It's different with machine learning. Okay? So this is what you're telling the machine about the world right here. So our job is to try to predict the target given the features. Okay. Now the machine says, you know what? I don't live in your world. I don't understand what this means. This is for human eyes. I don't know what that is. Just give me the numbers. That's what the machine says. And sitting between the examples is some machine learning algorithm. See, machine learning isn't you. You asked a question about heart disease. You came up with examples. You gave it an answer key, and go home. Let this algorithm sit between there and learn the pattern. You can't do it. You can't see all that data and learn. Okay, so this algorithm is going to sit between your examples of the world, like we did earlier. Here's the input, here's the output, and it's going to study it. It's going to look at your examples, assume you've told me the truth. Okay, she said, and this is what you're sure this is what I need to know about your world. Okay, then get out of my way. The machine's going to say, okay, let me see. Because that person has heart disease. Okay, that person doesn't have heart disease. Okay, that person doesn't, and that person does. The machines are brilliant at this stuff. I think you see 1 billion of them instantly, all of it. Okay, but I'm going to give you an example, like what we were doing. Now, once you do that with this, the machine says, you know what? Just give me the numbers. Put the features in the X, put the target in the Y. Pareidolia. Can you see what heart disease looks like, machine? That's what we're doing, pareidolia. You can't see anything as a human, but the machine will be able to see it. Of course I can see what that looks like. Of course I can tell it's a fraudulent transaction, or yeah, you get the home loan, or that person has benign cancer, or would this treatment or this medication, remember precision medicine, this would work best for this one, not so much for this other patient, or whatever it might be. Hey, pareidolia, can you see it, machine? Okay. And so once we do this right here, let's back up a little bit. See this right here, this target variable? What if you don't have a target variable, which happens a lot in precision medicine? Sometimes you just have a bunch of data, genomic data sets or something. You just have a bunch of data. I don't have an answer key. I don't have an outcome, but I have some beautiful data. What do we do then? If you don't have an answer key, that's what we call unsupervised learning. Okay, I can only classify or cluster based on some similarity of features. That's all I can do. Okay, that's unsupervised learning. Let me give you an example. Let me make it clear because I don't know everyone's background, so I'll go kind of back and forth a little bit, but people tend to know music. So let's say you have music. You're on Apple Music, okay, or Spotify or Netflix. It could be any service like that, okay? They're going to recommend stuff to you because they want to delight you to keep you paying your subscription, whether you know it or not, but that's what, with some machine learning algorithm. They want to put some stuff in front of you that delights you. And it depends on the person. Some people might need one movie every week to keep paying their subscription. Some people may need one good movie a month. It just depends. But the point is they need to find some stuff for you. Okay. So when we have this, the first thing you're going to tell the machine, because you live in the world, well, machine with music, I know you don't know about much about music because you don't live in our world. But we have these things called songs. I'm going to give you a song. I'm going to give you the artist. I'm going to give you the genre. We might have a bunch of other features, the danceability, the tempo, the duration. We have a bunch, but let's just say we have some features. That's X. Describe your world to me. Okay. And the machine's then going to say, now, what do you want me to predict? Oh, yeah. I want to know whether I will like a song. That's Y. That's the target variable. Then the machine's going to say, well, do you have examples? Do you have labels? Oh, yeah, of course. Yeah, see, I like this song. I like this one, this one, this one. Didn't like this one, didn't like this one, really hated this one. Can you see it, machine? Period. Oh, yeah. Can you see what I'm into? The machine wants feedback, knowledge of results, like your professor giving your midterm back. He or she is supervising your learning. Okay, I need feedback. Ooh, I didn't think you'd like that song, but you did. How you like that song, huh? Okay, then somewhere I'm wrong. I got to adjust my internal parameters and I'll try again. And then I'll try again. And before I know it, ooh, you're playlisting a lot of the songs I'm recommending. You're not skipping stuff as much anymore. I think I got you. That's your machine learning model. Only for you. Only you. A good song is only what you say is a good song. And that's what every machine learning model is trying to do. But what if I don't have an answer key? I have a bunch of music. But I don't know anything about you. You just joined my service. That's the cold start problem. You just joined Netflix. I don't know anything. What movies would I recommend to you or music? And that's where we do unsupervised learning. Supervised learning, have an answer key. You're going to supervise the machine. No, machine. Remember, I don't like that one. No, remember, machine, I don't like that. Or, oh, no, remember, machine, that's the kind of stuff I'm into right now. Yeah, I'm kind of into chill music a little bit. Nope, I know it's a little bit slower, but remember, whatever, just give me some feedback and I'll learn it. Okay? Unsupervised learning, I don't have an answer key. I have a bunch of data, genomic data, clinical data. I don't know the outcome. Can you help me out based on some similarity of features? Because certainly someone who has benign cancer, their feature should be different from someone who has malignant cancer. Or someone who has some genetic profile, there should be different outcome, maybe from someone who has a totally opposite profile or whatever. I don't have outcome. You have to find that form because you can see it all. That's unsupervised learning. Okay? So with unsupervised learning, if I don't know anything about you, for example, with music, I can just say, you know what, if I know the city you're in, I can cluster and just say this genre was kind of hot in your city. Not nearly as good as if you told me, right? That's supervised learning. It's better if you told me what you like. But if you don't, I can kind of try to cluster and do my best. Or if I knew when you were born, maybe I could give you some from a certain decade. Not nearly as good if you told what you like. See, so oftentimes unsupervised learning is inferior to supervised learning, but sometimes it really serves a purpose, and you'll see what I mean in a moment. So supervised learning, we typically call, as someone said earlier, regression and classification problems are supervised learning. And they're supervised learning because it has an answer key. It can learn because it knows the outcome. It knows this person's diabetes, not diabetes, so it can learn it. That's what's supervised. Unsupervised, again, I have a bunch of patient data, but I don't have any. Can you cluster for me? So let's look at unsupervised learning. That's today, the rest of the time, we're going to talk about unsupervised learning. Next time, we're going to focus a lot on supervised learning, which is really the best that we have is supervised learning. But I'm going to start off today with unsupervised learning. Okay, because a lot of time I'm going to talk briefly about smartwatch data, and typically we use unsupervised learning for smartwatch data. Because we don't have an answer key. It's just data that's flowing from my watch. I don't have any label to give you. Can you discover some unique groupings in my data and tell me some stuff about me or whatever? One of the most common algorithms But unsupervised learning is K-means. Remember what I said, don't memorize. I hope you have a mental model. I think it's so important to show you guys visually so you lock it down. If you remember the term, that's good. But I hope you have a mental model of how that works. K is used a lot in machine learning. I'll show you what the K means, and you're going to see what the mean means in just a moment. So K-means says I have a bunch of data machine. I don't have labels though. I have all these breast cancer patients' data, tissue morphology measurements, but I have an outcome. I don't know whether it's malignant or whether it's this, or I don't know, but I have a bunch of data. Or I have a bunch of genomic data. I want you to discover maybe some genetic variants within this. Can you discover that for me? Because I just have data. You can see it all. I can't. There could be millions of features when you're looking at genomic data. Okay, so the point is, I'm human. I'm finite. But I know you can do it. And so these algorithms can be very helpful in that. So we want to cluster the data based on the feature. Now, here's what I hope you can see. And I don't want to take it for granted. When I say a feature or a dimension, we're going to put the data out. Now, stay with me, because this is very important going forward for machine learning and unsupervised learning. We're going to put the data out into n-dimensional space, n, okay, like a nutcracker or something, n, the letter n-dimensional space. And n says, how many columns do you have in your data? How many features? If you have 17 columns, you're out in 17-dimensional space. We can only see 2 or 3 dimensions. Machines see in infinite dimensions. So I'm just going to show you 2 dimensions. Maybe we take a person's age and max heart rate. The point is, we're going to put every patient out into n-dimensional space. That's all of your patients. Go over for your age and up for your max heart rate. Let's just say if that were it. So one person, if they're older, they go way over for the age, up for max heart. Someone else who's young wouldn't go as forward for age, and maybe they don't go up as high for whatever. So they're all out in this n-dimensional space. Okay, and so maybe we want to group or cluster patients based on their maybe genomic variants or whatever it might, whatever question. You're the person going to ask the brilliant question. Here's K-means, though, that I want you to get. Probably the most common unsupervised learning algorithm. You do yourself a favor if you have a good sense of it, even if you remember the term K-means, because the algorithm is simple. And the first thing it does, you might tell them how many groups you want. You might say, you know what? I think I'd like to have 3 groups in my data. That's what K comes from. How many means do you want? Okay, so I'm going to say 3. If you say, give me 3 means, randomly, it puts what we call centroids or data points out in this n-dimensional space, just randomly. This is another data point, or we call it a centroid. This is centroid, and this is centroid. So random, you said you want 3 groups, right? Okay, here I put 3 data points randomly out into n-dimensional space that we call centroids. The algorithm then does this. Patients, or data points, patients, which centroid are you closest to? And I'm going to talk about how to measure distance in a moment. You belong to that group, that subgroup, whatever it is that we're going to determine about that, how to treat them, what treatment they'll respond better to. Maybe they have a more aggressive form of cancer. Maybe that, whatever it might be. But which centroid are you closest to? You belong to that group. Then the algorithm says, centroid, move to the average location of the patients in your group. Hope you guys can get what I'm saying, the location based on age and blood pressure and then cholesterol, all those. If you do all that, that's a vector. Okay, so it says go to the average location of these data points, or go to the mean location. That's why it's called K-means. It's the average location of everyone in your group. Then the algorithm says, hey, patients or data points, which centroid are you closest to now? You'll see some of these change groups. Centroids move to the mean location of your group. And you're looking here. Patients, which centroid are you closest to now? Move to the mean location of your group. Which centroid are you closest to now? They'll continue to train, move to the mean location of your group. You'll see some continue to change. They'll do this almost instantly, but just to show you that's K-means. Really easy to understand. But it groups you based on similarity of features. If your features are similar to mine, similar age, similar weight, similar height, similar race, we're probably similar. Doesn't mean we're going to both necessarily have diabetes, but we're very similar physiologically. Now, there's other things. Our DNA is different, our environment, our experiences, and stress, and other things that may be able to contribute. But in general, it says you two are very similar. So that's what it's measuring. So we're going to be in the same group. Okay, so this is K-means. Now these people these people have a genetic subtype for breast cancer. We may want to treat them differently, or maybe this group has a very aggressive form of breast cancer based on their features, or maybe this group right here responds favorably to a specific form of cancer treatment, or whatever. But we want to group them because I don't have an answer key. I just have data, and if you could group them by similarity, that might allow me to address them more specifically. Okay, now let me talk about how we measure distance. I talked about one patient is closer to another. Let me show you how we measure distance here. So here we have we have different patients, patient A, B, C, and D. And these are different features, feature one, feature two. Again, remember, these could be, if you have 25 columns, you have 25 features. I'm just showing you two, because for humans, you can visualize two dimensions. Okay, so this could be whatever age and resting blood pressure, whatever it might be. These are just two features. But I want you to see what I mean when we put something out in n-dimensional space. Okay, so here we have patient A and patient B. This is called Euclidean distance. You may have heard of it. When I'm done, I'm certain you will have heard of it. But you may not know it as Euclidean distance. And it says patient A and B, how different are you guys on feature one, age or whatever it might be? Okay, how different are you on feature two? And so what it does, it gets the differences on feature one. It squares those differences, so we get rid of the negative. It sums those squared differences, and because we squared them, we take the square root to put them back into their original terms. I know that won't mean anything to you. You can't speak math. Presenters just sit with it by themselves without someone talking. But let me show you this way. Here's a vector, right? This person's vector is 3 and 7. If they had another thing, they would have 18 numbers in their vector. So this person's vector is 3 and 7. This one's 3 and 6. So this is Euclidean distance. It says patient A and B, how different are you guys on the first feature? And how different are you on the second feature? Okay, let's get those differences. Now let's square those differences. Let's sum those squared differences. Because we squared them, we're going to take the square root to put them back into their original terms. And we say these two patients are 5 units apart. We say, what in the world does that even mean, 5 units apart? Well, let's look at it here visually. Let's put them out in n-dimensional space. On this age axis, on this x, whatever this axis is, how different are the two patients? Oh, they're 3 apart. And what about on this other axis right here? How different are they? Oh, they're 4 apart. This is the square distance, 3 squared and 4 squared. Let's get those. Let's sum those numbers. Let's take the square root of those numbers since we squared them. And we say that these two patients are 5 units apart. This is the Pythagorean theorem. A squared plus B squared equals C squared. Take the square root of C squared gives us C, this hypotenuse. And that's how we're measuring distance, say if someone is like you. This Euclidean distance used a lot for a lot of things that we measure in machine learning. Okay, so I want to know some similarities. So you get Euclidean distance. So you never have to calculate it, but at least you know, okay, so you say a patient's like another patient, you're taking all those features and saying how close are they in this n-dimensional space to each other. Okay, that's how I'm measuring that you're like some other patient or some other, whatever it is, some other song or whatever it might be. Now remember with k-means, we put everybody in a cluster. You're in this cluster and you guys are similar in this way. And you're in this cluster and you're kind of this way. And you're in this cluster and you're kind of, you all were in your own unique cluster. But if you're in that cluster, you're all equal. Okay? I'm in the cluster that responds well to this treatment. And we're all 50 of us in this cluster are the same. We're all equal. We are labeled with red. We respond favorably to this treatment. There's no difference among us. Okay? You may not want to do that. You may want to have some differences within a cluster. Let me show you another one, which is hierarchical cluster. I'm going to show you all. I'm going to bring all this together at the end. Okay, right now, don't memorize, you guys. I just want things to go into your eyes as we go over this series. A lot of this will be brought together for you. So hierarchical clustering says, maybe I want to know the differences within a cluster. Just because you're in a cluster doesn't mean you're so much like another person in the cluster. So here's hierarchical clustering. It's this dendrogram, which is an upside down tree, right? And each of these, what we call leaves, is a patient. And it says, here's all of your data, right? Here's everybody. And as I move down this tree, it says, you know what? If you really want to know, these two clusters are more like each other than this cluster, if you really want to know. So if something responded, if they responded well, you might want to try it on this cluster before you try it on this cluster. This cluster is really dissimilar from these, but these are kind of similar. As I move further down the tree, here are your 3 clusters, as I showed you. But within this cluster, some people are more similar than others. These 2 people right here are very similar. And then this patient right here is similar to these 2. And then these 3 patients are similar to these 2 patients. You see what I mean? It has hierarchical clustering. So it tells me within my cluster, there may be some similarities going on. So let me show you visually what I mean. Put all your data out into n-dimensional space and using Euclidean distance, it's going to say, which 2 patients are closest to each other? Okay, it's going to say, oh, these 2 patients right here. Okay, let's fuse them together so you can see how hierarchical clustering works. Remember, k-mean just throws you all in a bucket. You're all in the same bucket. But this says, no. 7 and 5 are most like each other. Then it says, okay, using some distance measure, what's the next patient that's close to something? It says, oh, well, 1 and 6, okay, they're closest to each other. That's the next closest thing. So we'll fuse them. Okay, and then what's the next thing that's close to something? Oh, well, 8 is close to this one. What's the next thing? 4 is close to this. And what's the next closest thing? 2 is close to this. And then the next thing, 3 is close to this. And then 9 is close to this. And then they're closest to each other. That's hierarchical clustering. And so now, remember with k-means, it just put them all in the same bucket. But hierarchical clustering might say, if you really want to know, patient 5 is most like 7. Yeah, 7 responded to that. Person 5 is most like 7. And within this cluster, just so you know, 9 is least like 7 if you wanted to know. Or if this for music, you're really liking that song, 5 is very similar to it. Now, I would recommend all these songs to you, but just to let you know, 9 is least similar to 7. I don't know what you're into right now, but that's hierarchical clustering. So even within a cluster, I can say what is most like another thing. And that might be important to me. Okay. And then the last thing I want to show you guys is this that you'll hear. And this is called cosine similarity. It's easy to calculate. I'm not going to talk about how to calculate it. Again, just mental model. Okay. You're almost never going to write this stuff wrong. You just have to have, you just need to know the tool to reach for. That's all you need to know. Whether how it's calculated is not going to matter. I'll give you a little mental model, but do I want to do cosine similarity or do I want to do Euclidean distance? We'll talk a little bit about that. But here's cosine similarity. It measures direction. Okay, where Euclidean distance measures magnitude, where cosine measures more similarity. I'll show you what I mean. You guys may remember the cosine unit circle. And the cosine unit circle, what is, you may remember from pre-calculus or trig. And it says if we have patient 1 pointing in this direction, okay, maybe go over 1 for whatever that feature is and go up 0 for this other feature. So it's over 1 and up 0. That's the direction of that vector. Again, you might have 25 different columns. I'm just saying if you have 2, go over 1 and up 0. That's the direction that patient is, whatever those features mean. That's where that patient is facing. Okay, their direction. Let's look at patient 2. Patient 2's vector is going in that direction. The way we measure, remember, go over age, over blood pressure, or cholesterol, or it could be genomic data, whatever it is. And what we try to do is look at the angle between the 2 patients' vectors. So you have to remember this, because it's going to be calculated for you. But if you do want a mental model, because most of you probably learned this at some point, you didn't know that you'd ever use it if you ever took trig or calculus. But we're looking at the cosine of this angle. Okay, that's what we're doing. For example, if patient 2 were pointing the exact same direction as patient 1, or 2 movies pointing in the same direction, okay, you're gonna, if you like a Toy Story, you're gonna probably get, some other, I don't know what it would be, monsters recommended to you too, because they're very similar. They're gonna be pointing the same direction in terms of their features and who stars in them and anime, all these types of things. And so this is oftentimes used for recommendations. It's used a lot for large language models. I won't get into that here. We do talk, I think our 4th talk on large language models. But the point is we have these 2 patients pointing in the same direction. The angle between them is 0. And if you remember, the cosine of 0 is 1. So we'd say these patients are extremely similar, if not identical. Now, let's say patient 2 is pointing in this direction. That's 90 degrees, what we call orthogonal. Okay, perpendicular, this orthogonal right here. And you may remember that the cosine of 90 is 0. There's no relation with those 2 patients or that treatment in this thing or that that subvariant of in some genomic profile, whatever it might be, they're dissimilar. There's no relationship. Now let's say patient 2 is pointing in this direction. Well, this is 180 degrees. You may remember the cosine of 180 degrees is -1. And that you would say those 2 patients are diametrically opposed, completely opposite. Okay, if something worked for this patient, I'm just saying theoretically, depending what the case is, they are opposites. It didn't work with this patient, but I'm not mad. I wouldn't mind. Let's try with this patient because they're very opposite. They're different. Okay, so that's what we do. So that's how we can. This is cosine similarity, and I'll show you how we use all these in a moment. Okay, now we're almost winding down. With all of that background, I want to make this more real for you. Hopefully, you have foundation. Machines learn by example. Okay, your job is to get examples of the world. Okay. The other thing is asking a brilliant question. And now you have all these similarities. If I don't have an answer key, which is what we're talking about today, I know how to measure distance, which will tell me this cosine similarity, or even hierarchical clustering. If I want to know even within all those little things that you don't have to remember, we're going to say it enough over our time together. But let's bring this together with some data sets as we wind down. Let's say you have some smartwatch data. Okay. Many of you probably have a smartwatch or are familiar with it or can get access to it. I'm not going to talk much about any specific data set today. We're getting close to our time, but smartwatch data is time series data. You can monitor individuals continuously in real time at all times. If you wear a smartwatch, I can tell you what time you woke up this morning. whatever it is. I mean, it's constantly monitoring you, And so with this data, this might be what smartwatch data looks like. So we have this streaming resting, this happens to be resting heart rate, where your steps are 0. And so I want to know something about your rest. If your steps are 0, your heart rate should be within a certain range. If your steps are 0, I mean, there's other things that could physiologically stress you. But in general, I'm going to say you're resting, say between midnight and 7 a.m. Okay, I'm going to get your resting heart rate. Okay, because it takes away all the issues if you're up during the day. Maybe you're running up a flight of stairs. Maybe there could be other things. But I'm saying, no. This is between midnight and 7. You're not taking any steps. Your heart rate should probably be within a certain range. Now, the resolution varies of your watch. It could be every few seconds. It could be every minute, whatever. I won't talk about that, but these are heart rate. You can see all of these. And if you do this overnight, you might have 400 to 500 different measurements. That's streaming. And so knowing what we know now, you can analyze that data in real time, heart rate data. So typically we have this fixed size windows where we're analyzing the data for maybe an event that's going on, whether it's heart related or whether it's related to whatever it might be, or it could be some outcome that's going on. And we look at these sliding windows. It's still what we're doing is we're analyzing this data that's flowing in real time, 24/7. We're analyzing the data if you want to do that. Now, that's not always important. Let me give you an example, which is a study that was done. In fact, you'll see that if you go through the certificate having to do with pre-symptomatic and asymptomatic detection of COVID-19 using a smartwatch. For example, instead of taking all those 400 or 500 measurements, that may not be important. What you may want to do is aggregate them in some way, take the median of them or mean or something. So instead of having 400 or 500 per day, let's get it down to just one number, because that's all that matters. Okay, is maybe just one number for the day. In other words, when you're resting, your heart rate stays within a narrow range if you're resting. Okay, if you're in bed, you're sleeping overnight. And so this might be your last 30 days overnight. From midnight to 7, this is your mean or median heart rate. Okay, and overnight resting heart rate is relatively consistent in healthy individuals. They're within a relatively narrow range. And knowing that, we can look for anomalies. If your heart rate is elevated, I want to know about it because that's not natural. Okay, but there's a few reasons why your heart rate might be elevated. So here, as we're looking at streaming data, each data point now is a day as opposed to a few seconds. And so we could develop this real-time alerting system using some distance measure. And so now we're going to look at your streaming data, your baseline, and saying, I want to know, alert me if a heart rate is significantly different from what my normal baseline is. That's what this does. So now, as your data is streaming in, you're alerted to some aberrant heart rate that perhaps associated with COVID-19 or flu, some infection, because your heart may be needing to work harder to fight off that infection. Okay, and so that's how you get some pre-symptomatic or asymptomatic detection of something, whatever your question may be. Now, there's other things that can be associated. Maybe you're under stress for something, a bill is due, or something happened with your child in school, or you're traveling, or you had a little alcohol last night, or you had a really intense workout, or there's other things that can artificially elevate the heart rate. But in general, but you would know that happened. You would know, oh yeah, man, I really worked out hard last night and pretty late, and that might be why my heart remained a little bit elevated. You would know that. But assuming those things didn't happen, I want to know if something's going on, because this has been shown to be related to allow, with some success, pre-symptomatically or asymptomatically, to detect some form of illness, and many other questions. These are questions that you'll come up with. Okay, so let me show you now really quickly in a notebook. I'm going to show you this, but I don't want you to worry about coding or the notebook. This is Python. It's easy to learn, but don't worry about Python. This is not about coding. This is bringing everything together in a notebook as we wind down here. Okay, so if you do this and you're going to code this, okay, if there's one thing I'd be adding to my list if I want to do data, bioinformatics, or data, it'd be Python. Human readable, easy to learn, it's the language of data science, whatever it is, AI, machine learning, data science, analytics, it's the language if you're doing it. Although we're getting much better now with just asking a model to do stuff for you, because models can code, excellently also. But the point, so that's why I just want you to have a mental model. So here we have a data set. You may not know what any of this data means, and I didn't give it the answer key. So this is breast cancer data, and this is tissue morphology, just the tissue, measures of different tissue for breast cancer. And I didn't tell the machine whether the patient had benign or malignant cancer. So I'm saying, machine, got to help me out. I have all this data, but I don't have an answer key. We'll talk about supervised learning next time. I know the answer, but I withheld it from the machine. Okay, so here I'm going to put all these features out in n-dimensional space. There's 10 columns, so each patient is out in 10-dimensional space. Okay, I'm just going to choose 2 because we can only visualize as humans 2 or 3 dimensions, so I can visualize it for you, but the machine's seeing in 10-dimensional space. So when I take the patients, here's what they look like. You might say, okay, so where are the clusters? Well, I have to do k-means. You know how k-means works. And let's say I ask for 2 clusters because I know it's going to be benign or malignant. Give me 2 clusters, machine. So I'm going to use k-means using 2 means, and here's what it came up with. Here's the centroids. And it says these patients are most alike and these patients are most alike or dissimilar. And it gave me clusters. And I can say, okay. And now I want to use those clusters to tell me, well, who do you think is benign? Who do you think is malignant? And see how accurate it is. Now, the only other thing really quick before I do that, it's just putting all these people in one cluster, all these patients. I might say, wait. Look at some of these people are way out here. Maybe, can you tell me who might be more similar to another patient rather than just giving them a yellow shirt or would I put them in the yellow group? Can you tell me who might be similar? And so here's what I can do for that. I can do my hierarchical clustering. See, here's the clusters. You're green, you're yellow. Bye, or whatever. Or you can say, no, wait, I want to do hierarchical clustering. Here's hierarchical clustering. And it says, well, this yellowish group, did you know that 2 and 30 are most similar? Yeah, they're really similar. And 2 and 1 are in the same cluster, but they're not as similar as each other. Remember, this says 2 and 30 are most similar. And then 12 is really similar to 2 and 30. And then these 3 are really similar to these. See, that's how hierarchical clustering works. Okay, so maybe if something really worked with this patient, let me try the person who's most similar to them, or whatever it might be, or closest to them. Okay, so 2 is most similar to 30. 2 is not as similar to 1 or close to 1. And 2 is farther from 21. 21 is actually a totally different group. Here's what's nice, to give you the row number, or you can call it the patient number. Okay, this is hierarchical clustering. Now, one other thing I want to show you, here's the predictions. And it's making these predictions from these clusters, just based on similarity of features, you guys. Here's what this model did. It said, well, here's the predicted, here's the actual answer key that I knew. It said this one's benign, which was true, benign, malignant, benign, malignant, malignant. This one was wrong, predicted benign, and the true answer was malignant and then benign. So unsupervised learning can really still do well based on similarity of feature if you get enough examples. Okay, and they're differentiated. If it's solvable, at least by humans, then we can separate them. Now, lastly, let's look at cosine similarity. Because you might want to say, how similar are 2 patients? Okay, rather than just looking at them eyeing it or something, you say, well, tell me, quantify how similar they are. Remember I said 2 and 30 are very similar? Cosine similarity, look, it's almost 1. So these are almost identical. They're extremely similar in their features. Now, Ray, let me go back up here. Sorry for all the scrolling. You can't make any sense out of this as a human. That's why we let the machine do it. Those numbers mean nothing to you. But the machine can say, based on all those vectors that I'm looking at it right here, these 2 patients right here are extremely similar. Remember we said 2 and 1 were in the same cluster. It says they're not so similar, not nearly as similar as these 2. That might be helpful. They're in the same cluster, but they're not nearly as similar as patient 2 and 30 within that cluster. And then remember, again, sorry for all the scrolling, but 2 and 21 are in 2 different clusters. So you may want to say, well, how similar are those 2? If you didn't know, again, if you did hierarchical clustering, you're looking. But if I do cosine similarity, look, it's negative. It says they're almost diametrically opposed. They're almost opposites. Whatever that means to you. You have to determine it, but you can see how we can use these measurements to inform you, the domain expert. And how do you want to approach that thing? Is kind of quantifying things that you just could never see. As I said, when you look at genomic data, you have millions of features, and you just can't see those big numbers. But once the machine gives you insight, you can interpret the meaning, because machines live in a world. Machine just repeating back to you, and then you have to go in and interpret what this negative 77 or this negative, what do you want to do about that patient? You're going to have to make that call, or someone will have to make that call. And then I said, can you compare patient 1 to the first 10 patients? And patient 1 is exactly similar to him or herself, so it's a 1. And then you can just look through all your data and get similarity scores, and maybe you have a threshold. Give me all patients that are at least 0.82 similar or better or something, whatever it is. So again, what do you want to do with this data? Then lastly, we have wearable data. Okay, so here's the wearable data. So here's your wearable data. And again, I've just taken the median. So I have one number for each day. And as you have your wearable data here, here's it flowing in real time. This is where you're using your distance measure. So you're having all your data flowing in, and as it sees something that's far using Euclidean distance or something, this is significantly away from your baseline, and so it can alert you. There's some physiological stress going on, whether it has to do with infection or some other stressor or something, and it can in real time alert a patient using a smartwatch. Okay? So we're doing, yeah. So I went a lot longer than I wanted to, you guys. But let me wind down here. So first of all, let me remind you guys. So let me see. Oh, no problem, Allison. No problem. Let me just leave you guys with this. So I'll stick around if you guys have any questions. During this will be office hours, so I'll hang back. If you guys have questions for me about anything, if you're currently moving through your certificate, if you have questions about doing something, or like I said, just in general, a project or whatever, I'll hang back. But let me just remind you, every Monday, 5 to 6, we have office hours. So come hang out with me if you want. I can help you walk through something if you're working through a module. If you want to discuss a project or your career goals, or can I get there from here, or which certificate should I take, or I'm stuck on this problem, or can you help me with Python or large language model or deep learning or whatever it is that you're doing every Monday. Or if you just want to study with me, just say that gives me an hour a week where I'm committed to getting through a module every Monday, whatever it is. Just know every Monday, 5 to 6 Pacific time is office hours. Okay, so feel free at any time. Some people are more bashful in a larger group, but if you come by, you want to chat with something, I'm glad to do that. And then just so you know, the next talk, which will be next month, will be on supervised learning, which is the most prominent type of machine learning. We'll be looking at clinical data sets, and we'll discuss more your role. We're going to talk more about you now. What is your role? How do you prepare the data? How do you describe the world to the machine? What do you do to tell the machine better things? Maybe the data that you have is, maybe your data is dirty, you're missing values, or maybe you don't need all those columns, or maybe you want to tell it more things about the world. That's what we're going to talk about next time.